All right. When we left off on Monday, we were talking about product law. And the idea behind the product law is that if you have two independent outcomes and you want to know what is the probability that both of these independent outcomes will occur, you multiply the probability of one outcome times the probability of the other. And so if you have a penny and a nickel, and you want to know what is the probability that if you flip a penny and a nickel that they will both be heads, you take the probability that the penny will be heads times the probability that the nickel will be heads, and you get the probability that both will be heads. So you use this product law when you're trying to calculate very specific outcomes. So if you're trying to say, what is the probability that a pregnancy will result in a male? 1/2. What is the probability that two pregnancies will both result in males? 1/4. Right? Each pregnancy has the result of 1/2. And that's one thing that sometimes when people are first learning about these rules that they mistake. So if a couple is planning on having 2 children, they have their first child, it is a male. Just because there's a 50-50 chance of having male or female, it doesn't mean that they now have an increased chance of having a female for their second pregnancy. Every single pregnancy has the probability, the equal probability of male or female. And that's why you can have families that have something like 13 boys. And they keep trying for a girl. I'm like, just stop. Like, stop. The odds are the same every time. It's 50-50, but you know, the odds are not in your favor apparently. So again, you know, it was like my cousins. I have 3 girl cousins, and their dad, my uncle, he really wanted a boy, and they finally got one. So that's when they stopped having kids. But again, every chance. So it's the same thing if you have like the albino tigers. If they have, you know, the white tiger question, so you've got the normal phenotype, they have one that is albino. All of them could be albino. Just because there's only a 25% chance doesn't mean that they can't have a litter of albino kittens. So the probabilities might be lower, but they're not 0. And this is how you can calculate those probabilities. Now, sometimes you might be looking at what is the probability that something could result in a couple of different ways. And so this is basically when you have to add the probabilities together. And when we're using our coin example, the example is, what is the probability that we will get 1 head and 1 tail when we flip our 2 coins? Well, it's 1/4 that you would have a penny that shows tails and a nickel that shows heads. It's another 1/4 that you would have a penny that shows heads and a nickel that shows tails. So if you don't care which coin shows heads and which coin shows tails, you add those 2 probabilities together and you have a 1/2 probability that when you flip the 2 coins, you'll get the combination that you wanted. Okay? So this would be something like, if we, okay, let's look at what is, well, we can do our boy-girl example. Okay, so what is the probability that we will have 2 boys and then 1 girl? In that order, boy, boy, girl. So what is the probability that the first pregnancy will result in a boy? What is the probability that the second pregnancy will result in a boy? And then what is the probability that the third pregnancy will result in a girl? So here you're looking at a 1/8 probability that you'll get that specific outcome. But if you don't care so much as to whether or not in which order they come, you can add together, and instead you would get the probability of the two boys. So you have the probability of a boy. So you don't care in which order they come. You calculate the probabilities of all of them. So 2 boys, then 1 girl, that's one option, right? And that's if you want this particular order, it's a 1/8 probability that you'll get that particular order. But now if you don't care, you just want to have 3 children and you want 2 of them to be boys and 1 of them to be a girl, and you don't care in which order, you then could look at what is the probability of having a girl and then 2 boys. So the probability of the girl is 1/2, right? 1/2 for each of the boys. So it's 1/8 that you would get this combination. And then the other option you could have is you could have a boy, a girl, and then another boy. So each of these individual outcomes has a 1/8 chance of happening. So if you really care about the birth order of the children, there's only a 1/8 chance that you'll get the particular birth order you were looking for. But now if you don't care about the birth order and you only care about having 3 children, 2 boys, 1 girl, in whichever order they came out, any one of these outcomes would be sufficient for you. So you add them all together. So there's a 1/8 probability that you would have the boys, then the girl, plus the 1/8 probability that you would have the girl, then the boys, plus the 1/8 probability that the girl is in the middle. And so for a family that has 3 children, if we don't care about birth order, it's a 3/8 probability that they will have 2 boys and a girl, regardless of order. So you don't care about how you get that combination, you just care that you got it. And so again, those are different things that you can consider when you're calculating genetic probabilities. But again, you have to consider each individual crossing as its own potential outcome. So one of the questions on here was a certain type of congenital deafness is caused by a rare autosomal dominant gene. In a mating involving a deaf man and a deaf woman, could all of the children have normal hearing? If it's a rare autosomal dominant gene, the parents are probably heterozygotes. Could all of their children be hearing? Yes. Right? Because you cross one parent with the other, and it's only a 25% chance, but there's a 25% chance that a pregnancy will result in a hearing child. Every pregnancy has that same 25% chance. So the more children they have, the much less likely it is, but if they only had 1, it's a 1 in 4 chance that their child will be hearing. If they have 2, it's a 1 in 16 chance, because you start multiplying it together. It's the same thing. Can a couple have 13 boys? Yes. Is it likely? No. But it does happen.
Is there a chance that one of the parents will be
When you have a rare autosomal dominant, almost never. Most rare autosomal dominant conditions lead to what we call basically embryonic incompatibility. The fetus will not develop. So even with Huntington's disease. So a child that has, if a fetus has both autosomal dominant, the child is not born.
If the hearing child has children like a hearing person, would their child have the gene or no?
No. Nope. So that hearing child is autosomal recessive, right? So that means any hearing parent is also autosomal recessive. So unless there was a spontaneous mutation, there is no probability that the hearing child who mates with a hearing person will have a deaf child. So just because it's rare doesn't mean it can't happen. All right. So we also can calculate about our hypotheses. So when we're looking at genetic data, we're looking at crosses, we can formulate a hypothesis about what we think is going to happen. We can run our experiment, use the data we get to say whether or not we think our hypothesis is valid. And so to do that, we use a technique called chi-square analysis. So when Mendel does his crosses, right, and we say in the monohybrid with the heterozygotes, we're going to get that 3-to-1 phenotypic ratio. That is, it's a prediction, right, based on a Punnett square. We predict that 3 of the offspring will show the dominant phenotype and 1 will show the recessive. When we do the dihybrid cross and we see that 9-to-3 to 3-to-1 ratio, again, it's just a prediction that when you set up those Punnett squares, you should have 9 that display both dominant, 3 that display 1 dominant, 1 recessive, 3 that display 1 recessive, 1 dominant, and then 1 that displays both recessive. And again, it is based on assumption that each allele is dominant or recessive, that the alleles can segregate without any interference, that independent assortment occurs, basically the different chromosomes assort randomly, and that fertilization is random. And what we see with these asterisks is that sometimes when you leave things up to chance, you can see random fluctuation. Okay, so we all know that if you flip a coin 4 times and you get heads all 4 times, that's kind of weird, but not that weird. But if you flipped a coin 10,000 times and got heads 10,000 times, there's probably something wrong with your coin. Okay, and so that's what we're trying to account for with the chi-squared. Is any variation we see because of chance? So let's say we flip a coin 10,000 times and we get 4,500 heads and 5,500 tails. That's not quite our 50-50 ratio. So we can do chi-squared analysis to figure out, was it just chance that we ended up without a 50-50 ratio? Or is it possible that there is some other interfering factor that could have led to our outcome not matching our predictions? And so that's what we're looking at with chi-squared. Does our outcome match our prediction? If not, why? Is it because of chance or is it because of something else? And so that's what chi-square analysis does, is it looks at those numbers and tries to figure out, or try to help you figure out, whether or not any fluctuation you see is because of chance or because of some other factor that may play a role. And so that's why when you do experiments, it's really important to have a large sample size. So again, that idea of even if you flipped a coin 10 times and you got heads 10 times, kind of weird, but it could happen. But if you flip it 10,000 times, you should not get heads 10,000 times. That poor couple with 13 boys. I mean, I guess if they kept going at some point, right? If they kept having boys, perhaps there's something wrong with the husband's sperm. So you would have to do testing because it would begin to violate the laws of chance alone. But even though 13 kids sounds like a lot, in terms of sample size, it's really not that much. So if they were like, rabbits or kittens that have multiple offspring at one time and have multiple litters a year, you could get more sample size there. But with humans, sample size is low. And so that's why, again, when you're doing experiments, it's really important to have the statistical power to make conclusions about your data. That's why we make you take statistics. Not because we want you to suffer, but because statistics are critical for science. I mean, we all suffer. I suffered through statistics too. It was terrible. Hated it. Yeah, but it's important. Sorry. You do have to understand significance, and you have to understand experimental design in order to support your conclusions. So when you're looking at a set of data, one of the first ways when you begin to think like a scientist is you come up with your hypotheses. And so what you have is what they call a null hypothesis. And your null hypothesis is basically that your data will behave. If you cross P's, you will get that 3-to-1 ratio for a monohybrid cross, or that 9-to-3 to 3-to-1 ratio. And if you have a slight deviation from that ratio, it's probably just because of chance. The way the chromosomes segregated, maybe the wind blew and a different pollen got in. Chance alone is what might have skewed your ratios a little bit. And so the null hypothesis is, yeah, basically, I got what I expected. Now, with your null hypothesis and with the data you get from doing experiments, you can either reject your null hypothesis, or you can fail to reject your null hypothesis. Notice I don't say you can prove. In science, we don't prove, we support. Okay, so you can support your null hypothesis, you can fail to reject your null hypothesis, but you don't prove your null hypothesis. Okay, so how do we determine whether or not we can reject our null hypothesis or we cannot reject our null hypothesis? Well, we do this chi-square analysis. And if you have taken statistics already, you have probably done chi-square analysis before. You may not remember it, and that's okay. And you may not have taken statistics, and that's okay. So we'll go over chi-square analysis just a little bit. So again, this is a way to determine how well your observed data, you did the experiment, you got your results, how well does that match what you thought was supposed to happen? So let's say we are doing a monohybrid cross. So that'll be on the top. When we're in our hypothetical example, we are crossing two heterozygotes. So our expected ratio of phenotypes is that classic 3-to-1 ratio. Okay. So let's say we're looking at flower color in Mendel's peas. If we're looking at flower color in Mendel's peas, they can either be purple or white. So we'll set up a classic Mendelian experiment. We have a true breeding purple flower crossed with a true breeding white flower. This is our parental generation. Our F1 is all heterozygotes. They are all purple. And so we're going to set up our experiment to cross the F1. And of course, if we set up our Punnett square, this will give us our expected. So we would expect 3/4 to be purple and 1/4 to be white. Okay, so this is our F2. 3/4 purple, 1/4 white. Okay, so in our hypothetical experiment, we are going to generate 1,000 offspring. Okay, so if we're generating 1,000 offspring and I'm expecting a 3/4 to 1/4 ratio, how many of my offspring am I expecting are going to be purple? Yeah, 750. So I would expect 750 purple and then 250 white. So these are my expected results. Now, we did the experiment on the top, and we got our 1,000 offspring. However, we actually only had 740 that were purple, but we had 260 that were white. So our observed and our expected ratios do not match. Now, do they not match because of some unknown factor that could be playing a role in how flower color is formed in peas? Or do they not match just because of chance, right? Nothing's perfect, so you're not going to get the perfect ratio. Well, I don't know. That's why we do chi-square analysis. And so again, what this is going to tell me after we do the chi-square analysis is whether or not we're off by 10 on each because of chance alone or because of some random, I don't know, the way the stars aligned and then the plants didn't want to mate properly and color is weird, whatever. So the way that we do the chi-square analysis is we first look at our deviation. So we subtract the observed from the expected. So if we're looking at our deviation, basically how different is our observed result from what we expected. And so we would do observed minus expected. Okay, if we observed 740, but we expected 750, the difference is -10. And if we if we observed 260 white flowers and we only expected 250, the difference is +10. Then you just square that, so you basically square that difference, which makes everything positive numbers. So -10 squared is 100, +10 squared is also 100. And now you take that deviation and divide it by what you expected. So you do, so this would be the deviation, so you do deviation divided by expected. So you would do 100 divided by 750. You would do 100 divided by 250, and I can't do that in my head, so I'm going to look up here. Okay, so 0.13 and 0.4. So these are just basically the numbers that represent how far away we were. You add them together, 0.53, and that is your chi-squared number. Okay, so that's how you calculate the chi-squared number. You figure out how far away your observed results were from what you expected. So you do a little subtraction, a little squaring, a little division, and then you add those up and you get a chi-squared number. Okay, and I won't make you walk all the way through the dihybrid, but it works the same way. You can practice that at home. And what we're not going to talk about just yet is the p-value, but we'll get there. So that's how you do the chi-square math. And then the other thing you have to take into consideration is what they call the degrees of freedom. And the degrees of freedom is really just referring to the number of categories, or the number of basically types of expected outcomes. And to calculate the degrees of freedom, you take the number of categories or the number of expected outcomes and you subtract 1. So for our monohybrid cross we have only two options in our expected outcomes, purple or white. So in this case, n is equal to 2, but the degrees of freedom, remember, is n minus 1. So it's 2 minus 1, 1. So the degrees of freedom is 1. Now I'm going to ask you to extrapolate. Let's say we're doing this on a dihybrid cross. How many potential phenotypic outcomes are there with a dihybrid cross? 4. So what would the degrees of freedom be? 3. Awesome. Okay, so good. So now you know degrees of freedom. And then how do we calculate that p-value? Well, a little chart like this. So you would look at that chart there, and you look for your degrees of freedom. And so in our experiment here, our degrees of freedom is 1. So we're looking here, 1. And you're looking in this row where 1 is, and you're trying to find your chi-squared number. So our chi-squared number is 0.53. That's what we calculated over here. And again, you can refer back to the previous slide for exactly how we calculated that. So we look 1 degree of freedom, and 0.53 is going to fit somewhere in here, right, between 0.46 and 1.64. So you can have a very detailed chart. This one is kind of summarized. And then it tells you the probability. Okay. That's what's up here, where 1 would be the highest number you could have. And so our 0.53 fits somewhere here in between 0.46 and 1.64. If I recall that previous slide correctly, I think it said something like the p-value was 0.48. So, okay, well, what does that mean? So what? P is 0.48. Well, basically what that means is P is your probability value. So for example, it's giving you 0.26, but let's use our example, 0.48. So P is 0.48. Our p-value as a percentage is 48%. And that means that if you did that same experiment, getting 1,000 offspring and counting whether or not they were purple and white, however many times, you would expect that 48% of the time, the deviation due to chance would be less than the initial, meaning you would 48% of the time, you would expect to be even closer to the expected ratio. So really what you're looking at, if we go back to the previous slide, the classic p-value that people use in the life sciences to exhibit that they think something is significant and it was not due to chance alone is 0.05. So when they say a p-value of 0.05, they're basically saying there was only a 5% chance that what I observed was due to chance alone. Meaning there was a 95% chance that what I saw, the reason that my expected results were different from my observed, was because of some other factor. And so in this case, you reject your null hypothesis. When your p-value is so low that it was likely not due to chance, that means you can reject your null hypothesis of it was due to chance alone. So if you ever begin to read scientific literature and you see people say these are significantly different or this has a significant effect on that, they've chosen this magical p-value of 0.05. but still, I don't know if I'd want people to be making decisions on health and things like that. Well, there's a 5% chance. I'm like, still too much. The smaller that p-value is, the more likely that an experimental condition or an experimental modification would have been what contributed, not just chance alone. So that's how you can do the math. So again, p-values enable us to reject or fail to reject our hypotheses. So this, if you see a p-value greater than 0.05, that means that it's by chance alone, basically, is what they're saying. And so you do not reject your hypothesis. You want it to be less than 5% probability of chance alone in order to reject your null hypothesis. That's how they're like, oh, I'm sure, I'm really sure. And if you do get into doing scientific research, you'll find people do what's called p-hacking. There are lots of ways to set up your statistical analyses in order to get a p-value that looks the way you want it to look. So don't necessarily trust people's math. Trust but verify. Do the math yourself. Based on the table. This table is condensed, but you can get degree of freedom tables that will have all of the p-values listed, and it'll tell you exactly what your chi-square value is. So our chi-square value was 0.53, meaning that our p-value is going to be somewhere between 0.2 and 0.5, because that's where 0.53 fits on the table. So you look at your degrees of freedom. So for every experiment, it's going to be different depending on your degrees of freedom. So you go with your degrees of freedom, and you scan across and look for where your chi-square value fits, and that's how you pick your p-value. So we will pick up with pedigrees on Friday.